Simplifying color and kinematic structures of QCD.
I thank the organizers for the invitation to speak here. I'll be talking about simplifying color and kinematic structures of QCD. And this talk is based on my work with, mostly based on my work with Henrik. And since this is the first talk on a color kinematics related subject, this conference, I have the honor of giving an overview of the situation with the color kinematics values in the double copy. So let's start. In Yang-Mills theory, we have gauge bosons that have structure constants as the basic fun rules. So these structure constants obey the Jacobi identity. At the same time, we can allow for fundamental matter to be coupled to the Yang-Mills gauge bosons, and fundamental matter obviously has a basic commutation relation. And both these relations are nicely represented in terms of color graphs and look quite similar. In this way, these basic relations introduce the color algebra for color factors, and they can be also, these graphs can be considered inside of more complicated graphs and induce color relations at high multiplicity and loop order. Once this is done, we can use the fact that all high point interactions like chordic vertices also can be decomposed in terms of these color structures that are completely trivalent. And thus we can absorb all chordic interactions in a trivalent graphs. Once we've done this, we can take all the algebraic identities that we know are true for color and impose it on kinematic numerators. They're just defined as everything that's kinematic apart from the inverse propagators that are scalar functions, momentum. So once we ensure that the kinematic numerators obey the same algebraic identities, we talk about the color kinematics duality. And one of the main corollaries of the duality is the double copy construction for gravity amplitudes. So now here it's the L loop amplitude written in terms of the cubic graphs level of the integrand. And once the color kinematics duality is imposed, we replace the color factors by the numerators, and the duality ensures that the final object is gauge invariant and constitutes a sensible gravity amplitude. Since I've introduced a duality for a Yang-Mills theory which couples to matter, we also have an extra structure to play with, so we can not only just multiply it by a numerator, but we can also consider a slightly different double copy when we introduce a bar here. So we take the second copy of the Yang-Mills numerators, in which we flip all the fundamental arrows, and in the massless case we can fix the helicities and flip them as well. And this kind of double copy can give us gravity amplitudes in a theory which has abelian matter content coupled to the gravity. And this abelian content can be even tunable with this factor nm here, which is taken to the power of I. Well, absolute value of R is just a counter for the number of fundamental loops in either diagram. And this factor here basically gives us a tuning parameter to change the number of complex matter multiplets. And here you can also see that the actual number is nm plus 1. So if we restrict ourselves to the pure joint double copy and take nm to be 0, then we still have one complex matter multiplet running into loops, for example. And to get rid of them, if we want to get rid of them, we can actually get rid of them by taking nm to be minus 1. And this way, we introduce the -1 here, and we can talk about the dose prescription for double copies of pure gravities. But this is not a talk about pure gravities or the double copying principle. So I'll just show a spray of different color kinematic satisfying gauge theories that we know at the moment. And the resulting double copies are also quite numerous. And I look forward to hearing Marcus talk in which he'll cover a non-trivial part of this list. But in this talk, I will be concentrating on the applications of the color kinematics relative to QCD. And by QCD, I can in principle mean SUNC Young-Mills coupled to massive quarks with flavors. But in principle, it will also be true, what I will say will also be true for quite generic Young-Mills theories with fermions or scalars, with masses without and d-dimensions, and you can also introduce supersymmetry if you want. That said, the main ingredient that we have now is the fundamental representation that's complex, as opposed to the joint representation that lives in the pure Young-Mills, and that's trivial. And the second main corollary of the duality is the fact that once we know that the numerators can be taken to be color dual, to be color kinematic satisfying, we don't even have to know them to say that there are BCD relations for color ordered amplitudes. And this is a gauge invariant statement that can be used without actually knowing the color kinematic satisfying numerators. But before I get to that, I'll also discuss just the color structure that also becomes non-trivial when we have QCD with flavored quarks. And I'll talk about I'll introduce a new color decomposition for colorized amplitudes. So, but first of all, let me remind you that the familiar story at the level of pure gluonic tree-level amplitudes, when we know that starting with the n-1 factorial cyclic invariant primitive amplitudes, we can see that they still obey Lies-Perif relations that let us go to a smaller basis for n-2 factorial primitives and fix basically two arbitrary adjacent legs close to each other. And this basis can be further used to write a color decomposition for the colored rest amplitude, just in terms of this basis amplitude, with the color factor written as a string of structure constants for the pure gluonic case. And the structure constants, the string of structure constants is best represented by a half-lighter diagram, which is obtained by taking these legs 1 and 2 and pulling the whole diagram by them and letting all other particles stick out in the half-lighted way, and then the permutation sum will go over these unfixed particles. And I personally learned to appreciate this nice tree-level formula when working with Simon, Gustav, and Donald on two-loop integrants in pure Young-Mills, in which we, when we consider the full color two-loop amplitude, and just the fact that the tree-level gluonic amplitude obey this they can be decomposed in terms of this DDM decomposition, told us that when we use this decomposition inside loops on the cuts, we can deduce nice color structure, the full color structure for two integrants, just by following basically this this picture. So for example, in principle at two loops, there's two main topologies, cut topologies, and then we can start talking about polynomial reduction, in terms of polynomial reduction, about irreducible numerators for these topologies. And to construct the full color amplitude in terms of these topologies, we just need to use the DDM, like here, for example, when we have two internal lines and external lines, we take this internal lines to be fixed, and then we commute all other legs, and this gives us a correct permutation sum and the correct color factors. And when we go to slightly more intricate topologies, we still basically use the same DDM decomposition. Here I fix this leg, this leg, and this leg, and then the permutation sum is given by the DDM decomposition. And then so this is the general schematic at two loops, at endpoints, but at 5 point, with the 5 point to the amplitude, we could write the full color decomposition in terms of irreducible numerators and the color factors. The same calculation can be also regarded as a motivation for considering BCJ relations for three amplitudes, because that's exactly what we use to reconstruct the non-planar part of this amplitude called the planar part. So after this small two-loop aside, let's consider the goal of this part of the talk, which is, well, what's the color decomposition for the general case of 2K flavored quarks and n minus 2K gluons? And we want to have it in a DDM-like way, in a way where KK relations are already resolved. Well, fortunately, the basis with respect to the KK relations was already found by Amelia. And we call this Amelia basis because that's a very nice phrase. And this basis is basically, it starts like the KK basis. We fix two particles, two quarks, but the permutation that goes after these two particles is constrained by the quark structure that can be translated to bracket structure. So the brackets just means quarks and antiquarks. A bracket is opened by a quark and closed by its corresponding antiquark, and then with a 5-point case with two fermion lines, or after we fixed the first two quarks, the second two quarks can only form one bracket, just open and closing. And then the gluons just are inserted in all slots that don't break 1 and 2. But how the core bracket structure, how it works, it's easy to see. It's more illuminated if you look at the 6-point example where there's two unfixed quark pairs, and they already can form two kind of bracket structures: opening, closing, and opening, closing, closing. And after we dress them with quark labels, we get a basis of four color amplitudes. So this is the basis in terms which solves the KK relation. What's the color decomposition in terms of this basis? Well, we've looked at it and we've found this nice formula, which is not very nice in terms of human comprehension if you want to look at it, but it's quite nice in terms of mathematical implementation because it's just replacement rules. The next couple of slides, I will just show how it's applied in terms of the graphs, so don't look at it too much just algebraically. But what we've done, we've checked it analytically up to 8 points, but quite soon it was proven by induction by the same terminology. And this formula works in the following way. Well, here's the 5-point example again, where as I've said already, the basis is just 3 amplitudes. The corresponding color factors are now decomposition. For 2 of them are just single diagrams. But for the other one, for the third one, where the gluon 5 is inside the bracket 3 and 4, we have a nested structure. And this nested structure brings us this object psi2, and this psi knows about the nestedness. It knows that the nestedness level here is 2. So basically, at the level of graphs, it's just represented by a curly line that knows about the quark lines downstairs. And it follows on them in a way that it just sums over possible couplings to every one of them. So so in this case, we just have two color diagrams. More generally, we can define this color rule for this object psi with an adjoint index and the counter for the number of, or for the nestedness level, or for the number of tensor factors in this tensor product. And this psi just basically falls down on each single level underneath it. And more generally, for any multiplicity, we can write the full color coefficient in our color decomposition, just as one diagram using this color rule for size, and then some overall couplings that occur, or not. This color coefficient already looks nice without expanding it. So that's it for the colors. So it looks like we've gained some better understanding of the color structures. Now let's introduce the kinematics in the game. And for the case of the QCD with quarks, the simplest example is the 4-point amplitude with one fermion pair and two gluons. And here we have just 3 diagrams from finals. No conic vertex can be inserted there anyway. So we just have Feynman diagrams. So those are Feynman rules from a textbook. And the color factors here are just TA, TB, TBTA, and FABC, TC. So by definition, they just obey the permutation relation. C1 minus C2 equals C3. And the enumerators, well, we've written in them just in terms of Dirac spinors and massive propagators. And we can just check that the same permutation relation that automatically worked for color, it automatically works for massive fermions as well, which is non-trivial, and you have to use the Dirac equation basically and random oscillation. But one can check that it works out. And once we know this, we can deduce this nice BCJ relation for the amplitudes in the KT basis, which is just a very simple generalization of the massless result. However, well, at 5 points, things still look the same, especially if we introduce another quark line. We can just as well, from these 2 permutation relations at the level of kinematics, we can deduce this nice and simple BCJ relation. However, this is one relation that we managed to derive. And more generally, for the 5-point case, in presence of only gluons, we would have 4 relations. So here's the table of independent BCJ relations that we tend to get. So here we got 1, but usually for the gluonic case we have 4. So the generalization to the multi-quark case is not so trivial. Some of the relations cannot stay true just because there's too many of them. So what we found was that the right subset of valid BCJ relations that hold true for the quark-gluonic amplitudes are the subset of linear BCJ relations. They're linear in momentum invariance, but it's the subset where the particle that we pull through the label permutation. So here is the sum over the position of this label n. So this label n has to be a gluon. Among all the purely gluonic relations of this type, we only allowed to take the ones where the gluon is taken to go through everything. And then this subset holds true. All other linear BCJ relations are no longer true for the multi-quark case. So that's what we found, and it was these relations were proven to be true to any multiplicity by Dela Cruz using Weissel quite soon after that. So that was for the independent relations, but after we know what the relations are, we also want to use them. And one way to use them is just to solve them with respect to some basis. And here's the solution, which is now, well, the function f here is a well-defined function of momentum invariance. And there's a product here, so it's no longer, well, linear, it's a polynomial function of momentum invariance. But it's solved with respect to some basis. And the solution works in this way. So we start with 1 and 2 fixed still from the KK basis, or the melee basis. But then, in principle, we're allowed to have some gluons. So this alpha is a gluonic set. We're in principle allowed to have some gluons going after 2. And then, but any amplitude where we have the next quark being separated from 2 by gluons can be written in terms of primitive coordinate amplitudes where this quark goes right after 2. So in this basis, basically, we reduce the melee basis where all permutations that preserve the quark structure are allowed to the basis where only those are allowed where the quark, where this permutation starts with the quark. And this reduces the n-2 factorial of the key factorial basis to an n-3 factorial over to k-2 over key factorial basis. We can even plug this basis in our color decomposition and well, play a little bit with the with the summation signs and rewrite our color decomposition as a minimal decomposition in terms of this n-3 factorial and so on basis. But just that the main ingredient here is that the color factors are now mixed with kinematic coefficients, which is the price to pay for the smaller basis. So that's it for the kinematic story at tree level. So let me summarize by just showing this nice table. We used to know very well how things work at the level of pure gluonic tree-level amplitudes when AK relations reduced us to a basis of n-2 factorial and a nice DDM decomposition. So now we know the corresponding generic color decomposition. And now we also know which kind of BCJ relations hold for the massive and flavored quarks, and we know the right basis for them. And finally, the outlook involves hopefully interesting applications of both the color result and the kinematic result in future loop level calculations. Furthermore, at the level of the double copy, we can start introducing double copies with coordinate scale masses, and we're still we get to identify the resultant theories on the gravity side. Moreover, well, I've quickly mentioned the prescription for amplitude integrants in pure gravities, which involves this ghost prescription using the fermionic double copy, and that may be a nice way to revisit the UV divergence structure of pure gravities. And the spectrality of considering chiral Fermis in d dimensions might have a nice connection to the evanescent effects that Zvi Bern and his collaborators has taught us about. And well, hopefully you'll hear more interesting things about this topic from Marco next week. Thank you.
Thank you for a clear talk. I wanted to ask you about color structures. You mentioned that at tree level we have n-2 factorial color structures, And I was wondering whether you can comment on the situation at 2 loops, but not for 5 legs, but for an arbitrary number of legs, leaving all fields in the edge joint.
Just in that, well, anyway, I don't know the counting. We haven't done the counting. We just know this, well, you're talking about the color structures. No, yeah. What we've done was basically abandon the color ordered amplitudes at the level of at high loops. We just basically realized that considering color ordered amplitudes at beyond the leading color is not very helpful. Well, at least that's our opinion. And when we wrote this color position, we just used color factors in terms of just color diagrams constructed from FABCs. And the exact numbers that's hidden there in general, we don't know. We just have an algorithm which is summarizing this nice picture drawn by Simon, where we just know that you just start with the topology and use the iambic composition to create the correct color factors, and at the same time the correct permutation sum to go over. That's our point of view on this question.
Any other questions?
So can you think of the massive Paul case as a dimensional reduction from some higher dimensional mass as fermion?
Yeah. In principle, that's a very helpful angle on which to look at. So that's after you see that things work, you can argue that they must have worked just from dimensional reduction indeed.
Any other questions? Not the best things. Thank you again. Alex, anything?